Hello students, so now we'll start with our next chapter, that is gravitation, chapter wise discussion of JEE Main 2025 January attempt. So now let's see our first question. So this is the first question, you can read. So what the question says is, a small point of mass m is placed at a distance 2r from the center of a big uniform solid sphere of capital M and radius r. So this is capital M and radius r without cavity, okay. For this, gravitation force on the P point of small m mass is F1 by capital M. So F1, what can I write down? F1. F1 is what? G m by 2r whole square, right? From the center distance is 2r. So this is my F1. Okay. Now he is saying a spherical part of radius r by 3 is removed from the big sphere as shown in the figure. So r by 3 radius, a sphere is removed. Okay. And the gravitation force on small m due to the remaining part of capital M is found to be F2. Okay. So this is mass removal problem. So see how F2 will be calculated. F2 is basically this force which was originally by capital M. Okay. Minus, if I subtract the gravitational pull by this small m mass, this m mass which is removed from here, then I will get the remaining this, right? So total was there. Then if I subtract the gravitational pull of this on this point, then I will get the remaining, right? So minus G m. Now what is the m? What is the mass here? This mass r by 3 radius, right? So uniform density, if we consider, then we can say density will be how much? M upon 4 by 3 pi r cube, right? Multiply by the volume of that particular, what we say, this cavity. What is the volume? 4 by 3 pi r by 3 cube, right? Radius is r by 3. This is the mass of this cavity into small m divided by distance. Now see the distance from the center of this cavity till here. What is the distance? This is r and this is r by 3. So total 4r by 3. So this is 4r by 3 whole square. Understood? Now see how much F2 came if we little bit simplify it. Okay. No need to that much simplify. Just see here how we can do. Here this is 1 by 4th of G m by r square, right? And here if I take common G m by r square, what is there? This is 1 by 4 minus, how much is this? 4 by 3 pi. 4 by 3 pi cancel out. This is 1 by 3 cube. So 9 3s are 27, 1 by 27, and this will come, this is 1 by 27, and this will come 4 4 16, and in numerator it will go 9, right? Okay, that's it. This is what I got. Okay, now calculate the F2, this numerical value, m by r square. Okay, so if I solve, what I get, no need to solve that much. See how. If you take LCM as 27 into 16, so you will get here 27 into 4 minus 9. Okay. And then after, if you divide, what he is asking, F1 is to F2. Okay. F1 is to F2. F1 by F2 he is asking. So means this will get cancelled out and numerical only. So 1 by 4. Okay, and then divide by this, means this will come in denominator, this will go in numerator. So means 27 into 16 divided by 9 if you take common here. Here if you take 9 common, this is 3, this is 4, 12, 12 minus 1, 11. Okay, this is what comes. So here, I will use another pen. This is 9, 3, okay, this is 4, 4 3 is 12. So this is 12 by 11. That's it. If you can solve, this is numerical calculation. That's it. The main part is this only, writing the mass of that cavity. Okay. So what I wrote here, this is density. What is this? This is density. Density into volume. Okay, of that cavity. So this is mass, and the distance from the center of the cavity till here. Okay, till the P point. That is this 4r by 3 square. Okay. That's how that I got 12 by 11. So answer is your first option. Okay. Now see the next question. Next, if a satellite orbiting the Earth is 9 times closer to the Earth than the Moon. Okay. what is the time period of rotation of the satellite given rotational time period of the moon is 27 days? The gravitational attraction between the satellite and the moon is neglected. Okay. See what he is saying is basically for moon the time period is 27 days. Okay. So time period is what? 2 pi by omega. Okay. Let's say this is the earth and this is the moon. Okay. There is a certain distance, right? Let's name it r, small r. Okay. So I can write down gravitational pull is equals to mr omega square, right? That I can write down. So I can say for the moon, this is moon. Okay. For moon, I can write down that gravitation pull, that is G m by r square, small r square, is equals to mr omega square, because I am dealing with the time period, right? So I will go for the omega. So mr omega square. Okay. From here I got omega square is equals to what? M got cancelled out. This is G m by r cube, right? Okay. This is for the moon. Okay. Understood? So if I put the value here, what I got, that time period is equals to 2 pi by omega. Omega, if I put, this will get capital G, capital M, and r raised to power 3 by 2. R raised to power 3 by 2. That's what I got. Okay. Now what? See, this is the formula which is kept. Okay. Now he is saying that if the satellite is 9 times closer, okay, means r is what? R by 9. Okay, then what will happen? So for the moon, this equation is like this: 27 days. Okay, I'm not cancelling out the converting in the seconds. No need, because the final answer of the other time period also we have to calculate in days only. 27, okay, is equals to 2 pi by gm r raised to power 3 by 2. This is for the moon. For satellite, capital T is equals to 2 pi by gm r raised to r by 9 raised to power 3 by 2. Okay, that's all. So you have to get the time period. Now if you see here, divide both of them. Okay, everything got cancelled out. T is equals to, here you will get 9 under root 3 to the power 3, 27. So 27 cancel out, this will come 1 day. Okay, because this is in 27 days, so this will also come in days because you are dividing everything. Okay, so your answer is 1 day. So your option second. That's it. Okay, just time period formula is. Now see next. Every question is just formula based. Nothing is too much like calculation wise, or even the half of the chapter he didn't ask. Okay. See next. He is saying about satellite only, gravitation force only, he did everything, and one I think escape velocity also he asked in one question. See now, a satellite of mass m by 2 is revolving around Earth in a circular orbit at a height r by 3 from the surface of Earth. See here, r by 3 is from surface of Earth. The angular momentum of the satellite is m under root g m r by x. Okay, so you have to answer the x. Fine. M by 2 mass. So angular momentum is basically, if you don't even remember, just see here, for a particle revolving in a circular path, okay, how you will write down the angular momentum? He's going at a tangential velocity, right? So just what you write down, m mass particle, so m, v and radius r, that's all. This is only the angular momentum, because these are r and v are tangential, right? Like perpendicular to each other already. So just you have to write down mvr, okay? So mass is m by 2. Okay, and velocity. So velocity, how you will write down? Because you know net mv square by r. So how much radius is revolving? Is revolving in 4r by 3. Okay, he said r by 3 radius from height from the Earth surface, like this. From here r by 3 height, going with a speed v in this orbit, like this it is. Okay, so mv square by r is equals to mr omega square. Sorry, mv square by r is equals to g m small m, that is m by 2. Okay, m by 2 divided by, hold on, so I'm putting here also m, leave it, mv square by r. This m by 2 I'm assuming is small m. Mv square by r, that is 4r by 3. Okay, is equals to, here g m by r square, right? So r is what? 4r by 3 only. 4r by 3 ka whole square. Okay. From here, if I get the velocity, what I got? Small m got cancelled out. Small m got cancelled out. This got cancelled out with the power, and v I got under root of 3 by 4 g m by r. Okay, that's what I got. Okay, so now what I have to get? Here, see, angular momentum, right? So angular momentum, for the angular momentum I can say mvr. V is what? Under root 3 by 4 gm by r into radius. What radius is this? 4r by 3. So 4r by 3. Now you put the value of small m also. Small m is capital M by 2, right? So capital M by 2 is there, right? Now see this 2 and this 4r by 3, because r is, if you see the answer, capital M under root g m by r by x, right? So if you see here, you have to take every numerical inside the under root. So you take this numerical 2 also under inside, so capital M outside, and then this will become 4 is 16, and this will also come 16, so this will also get cancelled out, and this will become 9, so this will get cancelled out. So g m r by 3 will remaining. Okay, so your answer is 3. For this question, x will be 3. You can solve for the numerical values. Numerically you can solve. Just put this small m as capital M by 2. Now take it. Okay, now take the numerical inside. Okay, then you will get your answer. Understood? Now see next question. Next question is, a satellite is launched into a circular orbit of radius capital R around the Earth. A second satellite is launched into an orbit of radius 1.03 R. Okay, the time period of revolution of the second satellite is larger than the first satellite. First one approximately by how much percentage? Okay, so basically time period only is talking about. If you see here, we have solved already for the time period relation. See here, this one. Actually in the Kepler's law we remember also this value, right? T square is proportional to r cube, right? But here we have the answer also, right? So we can say T square, this I will say some K. Okay, so what can I say? T is equals to some constant into r raised to power 3 by 2. Okay, now he is saying this is the time period in the first one. Okay, and for T2 what you did, K into 1.03 r raised to power 3 by 2. This is what you did. Okay, then he is saying percentage increment in the time period. You have to answer this. Okay, how much higher it is. So if you, what you will do, T2 minus T1 divided by T1, this into 100. This is your percentage. Okay, so get this value. What you will write down, T2 minus T1 divided, so K will get cancelled out, and you will have 1.03 r raised to power 3 by 2 minus r raised to power 3 by 2 divided by r raised to power 3 by 2 into 100. Okay, so r raised to power 3 by 2 got cancelled out. You will have here 1.03, right? So I can write down this as 1 plus 0.03. Approximately he said, so somewhere binomial approximation I can apply. Okay, so 1 plus 0.03 raised to power 3 by 2 minus 1 divided by 1 into 100. See this value. So 1 plus x raised to power n. So 1 plus nx, right? So what I will got? 1 plus 3 by 2 into 0.03 minus 1 into 100. 1 is 1 only denominator. This got cancelled out. Then 100 is there. So 3 by 2. So this how much? 0.3 by 2. So 945. 0.0045 into 100. Okay. So this will come 4.5%. So answer is third option. Okay, your answer is third option. Okay, now let's go for the next question. Just simple calculations, that's it. Okay, acceleration due to gravity on the surface of Earth is g if the diameter of the Earth is reduced to 1/3. Okay, diameter is reduced to 1/3 means radius is also 1/3. That's it. Of its original value, and mass remains unchanged, and the acceleration due to gravity on the surface of Earth is simple. This easier than this, nothing can be possible. G is what? G m by r square, right? Okay, this is small g. Then he is saying diameter is reduced to 1/3. So radius is also 1/3. So gravity will become how many times? 9 times. That's it. So G became G by 3. Sorry, R became R by 3. So G will become 9 times. That's it. 9 is your answer. Directly we can say. Okay. The acceleration due to gravity on the surface is space G. So space is 9 times. Okay. That's it. This is the fastest question possible. Next. Earth has mass 8 times and radius 2 times that of a planet. So some planet have a less 1/8 mass of the Earth and half of the radius of Earth. Okay, understand the question. Read the question properly. He is not having 8 times mass. He is having 1/8 mass. See, Earth has mass 8 times. So Earth has mass 8 times of it. Okay. If the escape velocity from the Earth is 11.2 km per second, the escape velocity in kilometer per second only from the planet will be. Okay. See here. Escape velocity, what we say? Basically, how we calculate the escape velocity? Kinetic energy that you gave plus potential energy at that point is equals to 0 plus 0, right? So we say Gm by R is equals to half V square, right? This is what you say. So what we can say from here, V is equals to what? Under root 2Gm by R. Okay. So from here we can say velocity for the earth, what is the velocity? 11.2 is equals to under root of 2Gm by R, right? And for the another planet, some planet V is there, right? So V is equals to under root 2, G is a constant, mass is what? Mass he said 1/8. Mass is m by 8. Okay, 8 came down denominator, and radius is 2 times, so 1 by 2. So R by 2. Okay, so this is 4. So if we bring it out, it will be 1 by 2. So V will be 11.2 by 2. If you divide both of them, you will get. Here there is a one more 4 factor is coming, right? Greater than this. So this will outside it will be 1 by 2, right? So it is 1 by 2 of 11.2. So that is how much? 5.6 kilometer per second. Okay. So 5.6 kilometer per second. So this is third option. Okay. That's your answer. Understood? Next. 7th question. Two planets A and B are orbiting a common star in circular orbit of radius RA and RB. Okay. RA and RB relation is given. The planet B is 4 root 2 times more massive than planet A. Okay. So first of all, he said that RB is equals to 2RA. This relation is given. Okay. And then he said MB is 4 root 2 times of MA. Okay. The ratio of angular momentum. Okay. He's asking LB by LA. LB by LA. Okay. So angular momentum. See, angular momentum also we have calculated. MVR, that's it, right? So angular momentum, where it went? Here. This was the angular momentum, right? This thing under root 3 by 4. Sorry, no need of this. You can calculate again. See, angular momentum is what? MVR. So MV square by R, whatever radius is revolving in. Okay. Angular momentum of planet B, the planet A, MVR, MV square by R is equals to MR omega, sorry, GM by R square, right? So how much is the V? So just we have to check the dependence upon the mass. Okay. G M, this M went. Okay. So this came how much? Gm by R under root. Okay. So here angular momentum, when you will write down mass of B into under root of Gmb divided by r of b, okay, radius of b into r, mvr, right, mvr, rb again, divided by, here you will have ma, mvr, mv is how much, gmb. For satellite he is writing, right, two planets A and B orbiting on a common star, okay, common star of radius ra and r, okay. So common star means this is not ma, see here, this is capital M is the mass of the star, so mass of the star is same, that's what I am thinking, how it can be possible. So G capital M, this will be, this is R, okay, so this is capital M and this will be, this is RB, this is RA, okay, and this is RA, this is how it will, okay, this is the mass of the star. So basically what is happening, there is an star, okay, with capital M mass, and there are two satellites, or you can say two planets revolving around him with mass MA and MB. There is a relation between the radius, and maybe A is bigger or B is bigger, I don't know. This is here radius, okay. So that's how it is. So this is capital M, so capital M is same. So what can I say here, that this got cancelled out. So MA and MB relation is what, MB by MA, and this will come under root of RB, under root RB, RB by RA, okay. So MB by MA, what can I write down, MB by MA, 4 root 2 from this relation, RB by RA, RB by RA 2, so under root 2, root is here, right, so this will come 4 into 2, 8, okay. So 8 is your answer. So for this, answer is your 8. Question number 7, answer is 8, okay. That's how. Just nothing. What was there? Two planets revolving around a star of capital M mass, you assume, okay. Mass of these planets are given relation, okay, and radius relation is also given. Angular momentum is what, mvr, that's it, okay. So that's what about this chapter. Thank you.